Hello, and welcome to the first lecture video for Chapter 10, which is the first chapter on heat. Thermodynamics is the name of the subfield of physics that we're talking about, and it covers two chapters in this textbook, that being the physics of everyday phenomenon, a conceptual introduction to physics, 10th edition, by Thomas Griffith and Juliet Brosing. So, what we're talking about here is, well, in this video, three definitions. Okay, just three definitions. Throughout the next two chapters, the laws of thermodynamics are going to be one of the big takeaways, and we'll leave off on this video just before the introduction of the first law of thermodynamics. And there's two, okay? So let's take a look at our introduction, all right? So we should ask ourselves, what are temperature and heat, okay? How do we define them, you know? We have an everyday word for work, right? You do some work, you get some homework done, but then we have the, of course, physics definition of work. We know that it's equivalent to energy, like kinetic energy. We know that it's measured in joules, right? So that's the type of question we're asking here. How do we quantify temperature and heat, right? They're separate, right? And, you know, are they the same? Are they directly related? Are they separate quantities, okay? And what causes heat? So how do we track it, right? How do we quantify heat flow from one place to another, all right? And we're gonna see that heat is energy. And we're gonna see that it flows from one place to another in one of three ways, okay? By the way, that's not gonna be the three definitions from today. That's another set of three for later on. And the three ways that heat moves from one place to another are conduction, convection, and radiation. So it's heat flow. Heat flow is energy flow, which is to say conservation. All right, that's the idea. So we can quantify it. We're going to see it quantified in joules. Turns out we're also going to see it expressed in calories, which aren't a terribly inconvenient unit. They're based off of a metric quantity of water, being 1 gram of water to go up 1 degree Celsius. So in that sense, they're very much tied in with the metric system with just an emphasis on water. So the calorie is a adjacent system, an adjacent unit to the joule, both based on metric measurements, but the calorie is specific to water, or it's customized to water to be used with, boiling water, water reactions, and so on, okay? So that's something to consider. We got another way to track energy that's just kind of unique or idiosyncratic to the discussion of temperature. All right, really temperature, or do I mean heat? Well, you always have one or the other, all right? What I mean to say is if you have one, you always have the other. So, but they are different quantities, okay? So definitely different units, different quantities. And as far as that goes, temperature is something new. Temperature is something we have not seen yet. It is a new base unit. In the same way that we've so far had base units of only 3, all right? The meter, the second, right? The kilogram. Everything has been in those base units. We now have a fourth, okay? So we've introduced a fourth. We'll have equations that are related to it with an appropriate constant that converts the units, so that maybe we have some constant, think the universal constant of gravitation. So that sort of constant. Imagine something that is like joules over the units of temperature. That in that way, you could multiply by it and cancel out and have a physically meaningful equation because you have the same units on both sides. So that's the idea. We're introducing a new base unit. So what is the base unit of temperature? It's not going to be Fahrenheit. Right? Fahrenheit is a measurement of temperature. It's going to be Kelvin. Okay? Kelvin is going to be the new base unit. Okay? It's the way we measure temperature. All right? So let's take a look at this slide here. So two objects are in contact with one another long enough, the two objects have the same temperature. Okay? This is actually sometimes called the Zeroth Law of Thermodynamics, which you see down here at the very bottom. I'm kind of cutting to the end here. So the Zeroth Law of Thermodynamics is that idea that if two objects, right, are, that if they're in thermal equilibrium, if they've been given sufficient time, that there's nowhere else for energy to flow because there's no net force acting on anything. Everything is at rest. Thermal equilibrium, at the end of the day, if we zoomed in at the microscopic level, is a force equilibrium, but on trillions of individual particles, okay? And a solid with all these elastic properties, whatever it may be. So these objects, though, in contact with each other, they reach an equilibrium. By definition, that means they have the same temperature. So essentially, we're extending a concept of energy and force, this idea that it's at rest, okay? There's nowhere else for energy to move. No accelerations left to happen, right? That aren't canceled out. That just aren't just in random motion. There's no net motion left. So that is, by definition, equivalent temperature. All right. So that's a strange way to define temperature, right? That it's all based on this concept that if two things have no heat flow left, no way to continue to flow, right? Equilibrium is reached, then that means by definition they're the same temperature. So I think we'll look for a better way to sort of maybe directly quantify or conceptualize the idea of temperature, but it's a great starting point. And it has a strange name, the Zeroth Law. That's because it actually came later. I got to get this completely worked out as a good reference fact, but as I know from word of mouth, and I'm pretty sure it's accurate, is that it did come later, and a good name that fit was the Zeroth Law because there was already the first and second. They were well known as the first and second. Okay. All right. So temperature scales. We're most familiar in the United States with the Fahrenheit scale. It's tricky to just switch over when somebody starts talking about whether it's 30 degrees or 35 degrees or 40 degrees Celsius. I'm not sure. I think 40 is really hot, or maybe it's fairly hot. So point being is that we can convert from one to another. We have these conversion scales. They're actually not perfect. This 5/9, it's an estimate, but it's fine for whatever question would be asked. And so because they're based on different standards, right? The metric system and the imperial system, the U.S. system. All right. Reasonable temperature scale, by the way, Fahrenheit, for describing everyday phenomenon. But the Celsius scale, much like my mention of the energy scale called the calorie, well, the Celsius scale is customized for water, right? So we've got a certain condition, which is considered, barometric pressure of 101,000 pascals, sea level barometric pressure, and then a certain temperature, which is going to be 20 degrees Fahrenheit, I believe, or 0, but one or the other in terms of the kind of the agreed upon temperature. Obviously, needing to be at the not phase changing into water, so I guess 0, but still as a liquid. But the point is that then there's an exact range then between 0 Celsius, meaning freezing, again with those pressure conditions met that I mentioned, right? And then 100 degrees Celsius, meaning boiling, so the phase change the water. So the scale is set, so you have that perfect 10 by 10 metric, base 10 system, not base 12 or something, right? Like feet and inches. And so you have a system that works, nice range, okay? It's a big deal though in terms that it does only work at a particular pressure. If you say, well, water always boils at 100 degrees Celsius, that's not true. If you're in a near vacuum, if you're in the incredibly low vacuum, water will boil at just a couple degrees. Believe it, like a couple degrees Celsius, negative Celsius even, right? You'll water boiling at closer to absolute 0, which we'll see is actually many, many hundreds of negative degrees Celsius. So you can have incredibly low boiling temperatures, that is, because it doesn't take much to go to that phase change. If the pressure's so low, water just naturally wants to. I mean, think if you expose it to a perfect vacuum, then you would need something approaching no temperature for it to boil, right? Because the water just wants to break apart because there's nothing holding it back. The water wants to individually break apart from that liquid phase to a gas phase, right? Exposed to a perfect vacuum, which is maybe, I guess, a way to start thinking about, which we'll talk about in just a second, absolute 0, okay? So by the way, what I'm getting at here, because I mentioned there's going to be 3 definitions, and I better tell you what they are, okay? Obviously, one of them is going to be temperature, okay? We're well on our way to defining it. We've got the Zeroth Law. We could stop there, but we won't. Well, there's another good way to think about it. Now, we're going to leave off before we really get to, like I said, the first law of thermodynamics. We're going to do these first 2 sections. And the other 2 definitions are heat, which I've already said is a form of energy, but we'll define it formally. And then this thing called specific heat capacity, which is really tricky with its name. It doesn't imply exactly what units it is. It turns out that it's a material specific constant. So it's one of those expressions that allows us to relate temperature, this brand new base unit, okay, that's going to be convertible to either of these. Or by the way, you'll see it on the next slide. So we got this brand new base unit, so we just need some constants to be able to convert. And the first one of those we're going to see is this thing called specific heat capacity. It turns out what it actually is it's energy and then per degree change per kilogram. So energy per degree change per kilogram. So how much energy it takes to change a degree for a certain mass of something. And so I say it's a material specific or substance specific quantity in the way that you ask yourself, is it water, is it oil, is it hydrogen gas, what is the thing that you're putting heat into? Well, then you know its specific heat capacity, you know how it behaves and how it behaves differently, because it turns out some things require a lot of energy to heat up, other substances don't require so much energy, okay? And somewhere in there, it doesn't specifically say, unless it does in the last description, there is a similar quantity, material specific, called the latent heat. Now that one is simply joules per kilogram, all right? And it doesn't even have a temperature change in it because it's strictly a phase change. And there's no temperature change when there is a phase change. So, or this, I may be misleading you a little bit because I think maybe phase changes are split in this textbook and I'm just mixing it up. So please don't quote me right now on that latent heat, but it will come up sooner rather than later. But it doesn't seem like it is here in section 10.2. All there is specific heat, okay? And specific heat has that rate of temperature, you have to divide by a change in temperature in order to get the correct number, right? You need a delta temperature. And those units of temperature. What are the units of temperature? Well, we got some candidates, right? Celsius, Fahrenheit. I outright said it's not Fahrenheit. Is it Celsius? No, it's that thing I said it's Kelvin, okay? So the 0 point on the Fahrenheit scale was based on the temperature of a mixture of salt and ice in a saturated salt solution. I think there was some experiments with phase changes. You can kind of get those multi-phase states. The 0 point on the Celsius scale is the freezing point of water, right, at a certain pressure. Both scales go below 0. And by the way, when I was speculating whether it was, what temperature is at, it was obviously supposed to be at 0. I was thinking more about like an ideal gas law situation. So obviously 0 freezing point of water at 1 atmosphere pressure. That's the Celsius scale. Okay. Both scales go below 0, so you can have negative Celsius happens on Earth. Lots of times people talk about space. We have some negative couple hundred degrees Celsius, okay? So, significant low temperatures. Maybe 150, I think, is going to be a lot of the ones in planetary science, like in our solar system. But there are some colder spots of space, for sure, and some very cold places that are created in small chambers in these ultra-cold laboratories that do ultra-cold laboratory science. They cool things down near a absolute 0, because there's such a thing, okay? So, absolute 0, what is it? So if a volume of a gas is kept constant, okay, while the temperature is increased, the pressure will increase, all right? This can be used as a means of measuring temperature, right? You can actually see, how much change there is, all right? So a constant volume gas thermometer allows the pressure to change with temperature while the volume is held constant, okay? The difference in height of the two mercury columns is proportional to the measurement of the pressure. Okay, so you're looking at that difference there. That difference, whatever pressure is created using hydrostatic pressure, which would be rho GH. So density of mercury is the rho term. All right, mercury is really dense. Was it 14,000 kilograms per cubic meter? I think it's 14 times denser than water, I want to say. So by far the most dense liquid found readily on the surface of Earth. Period, right? You can maybe some exotic liquids you could create. I'm not sure. All that aside, is the idea is that there'll be a line here and a line there. That height difference, right? In the depth, that height difference is a depth. The pressure that's created from that depth, so density times gravitational acceleration times h, which is just that value. That's what we're talking about. Okay, that would be the measurement of pressure. That's actually called a manometer. Very much like a barometer idea. manometer, barometer, see, that we talked about in the previous chapter on fluids. Okay, all that said is we have a device here that we can make measurements with. Also notice it's a very simple device. It's shown here like on a tabletop as you'd see it in a learning laboratory, but it could have been set up with equipment that was available a couple hundred years ago, and indeed in the history of these measurements, that's where these first experiments were made. Gases were observed, in flexible membrane chambers and so on, and the measurements were found that there was this linear curve for all these different gases, and they had different slopes to them, right? See here, different slopes. But if you looked at them and you looked at them all separately, you saw that they were all converging at a single point, okay? So they all had different slopes, yes, but they also had different intercepts relative to the arbitrary, in a broad universal physical sense, of choosing 0, because the 0 here is Celsius, by the way, okay? So, because that was the prevailing temperature method, right, when these discoveries were being made, so kind of in the progression of history here. We still use Celsius a lot because it makes a lot of sense to base things off these phase changes of water. But sometimes it makes more sense to base things off of this concept of absolute 0, okay? Because these different plots of pressure as a function of temperature, okay, right, and the idea that as things get cooler and cooler, the pressure decreases, okay, because we're holding that volume constant. So eventually we get down to a point where there's 0 pressure. Now that's actually a conceptual idea, and it's never been achieved, and I don't think physics has exactly agreed, but there's no strong support for that it is even such a thing to achieve absolute 0, because it would actually result in stopping motion. And it kind of seems like you can approach it asymptotically, right? But you can never actually completely stop motion. In the same way that, as far as we know, you can never cause anything with mass to achieve the speed of light, but you can cause small particles by strong releases of energy can approach the speed of light, but they can never get there. So maybe that's the idea of absolute 0, is you can get closer and closer to it, but never quite reach that idealized state of no pressure, which would mean no motion of the atoms that make up the gas, okay? And the value in Celsius is negative 273.2. So, okay, that's the absolute value. So obviously that doesn't work, right? We need a temperature scale that makes it obvious that this number is special, because otherwise it just looks like a mashup of numbers, right? So the temperature scale based off of absolute 0 is called the Kelvin scale, okay? And you don't say degrees Kelvin, you just say 0 Kelvin in the case of absolute 0. So absolute 0 in the Kelvin temperature scale is just 0 Kelvin, okay? Now, the great thing about it is that this scale, the Kelvin scale, was made to adjust the Celsius scale, but not completely make it useless for science, because a change of 1 Kelvin is identical numerically, right, to the change of 1 degree Celsius. That means any calculation where you need to divide by the change of temperature, which is a common thing that you do and a common thing we'll do, and you'll see, because that's a rate of change, right? If you're asking yourself, how much does it take to how much energy does it take to heat this up 10 degrees Celsius? Well, it turns out that same answer would be given to the question, how much energy would it take to heat this up 10 Kelvin? Because 10 Celsius and 10 Kelvin, it's the same temperature change, okay? It's the same delta. All right, you can't get anything colder than absolute 0, right? And like I said, it can probably only be approached but never reached. Okay, so far we've got a definition of temperature. Now we need to get heat and heat capacity. We'll be talking more about heat. Heat's going to be front and center when we have energy conservation, which is what the first law of thermodynamics is, because heat is our energy. Okay, it's more like work, by the way, because it's actually heat. Heat is energy in transit. And when we talk about containing energy, then you can actually possess thermal energy, which is just a form of potential energy, but kind of random, thermal energy in something that could be easily dissipated, right? Like a hot object, like a stone you heat up and put under your blanket to keep you warm or something, right? So that's releasing heat, all right? And that ultimately that's tied in what we're talking about here. I did hint, by the way, before I move on, I hinted at the idea that this Zeroth Law of Thermodynamics was good. It was a good starting point, but it wasn't the end all be all. I wanted to mention that if you read the section, you'll get an idea that temperature has another kind of formal definition, which is to say it's directly proportional to the average kinetic energy of the particles that make up that substance. So in a solid, it's everything jiggling around in some like molecular solid, and a gas, it's everything bouncing around, liquids, sheets of molecules and so on, some bouncing. So all of that is what we mean when we talk about temperature. It's this quantity that has an absolute zero. In the case of Kelvin, and that's the one that we defer to, and then it has its own rate of change, right? The fact that the one value is chosen as a new base unit, but it is proportional to something. The temperature then is proportional to this average kinetic energy. And then it's interesting because there's using mostly the mathematics of statistics. There's some models that are often called statistical mechanics, which is a subfield of the subfield of thermodynamics, okay? It being a subfield of physics. So within statistical mechanics, people get into exactly what these expressions look like for average kinetic energy for particles for different types of substances, different phases. All right? So that's how temperature ties in with existing units, because energy is based off of the other base units, all of them: mass, distance, time. Kilograms, meters, seconds. Now we've got one more, Kelvin. That's it, right? Physics is a language of very few letters. That's what its goal is, right? Break things down to the most indivisible fundamental facts. So, with that in mind, heat capacity is probably not one of the most fundamental facts, but it's useful for understanding for certain everyday phenomena. So what happens when objects or fluids at different temperatures come in contact with one another? Well, they start flowing. What starts flowing? Heat starts flowing between them, right? Usually in a big mixing case, right? In the case of fluids stirring together, but more ideally, maybe two blocks suddenly touching each other. Heat's going to flow from one to another until equilibrium is reached. Equilibrium being no more flow of heat, right? No need to, right? No net force, because it's the same temperature everywhere. Or maybe vice versa, it's by definition, it's the same temperature everywhere. Okay? So what is it that flows between them? That's heat. Okay? I definitely, said that already, jumped ahead of the slides. Okay? So heat flow is a form of energy transfer between objects. 100 grams of room temperature water is more effective than 100 grams of room temperature steel shot in cooling a hot cup of water. The reason being is because that steel, right, to reach that temperature, right, of room temperature, didn't take as much energy to get there. It was easier to heat it up. That means that essentially it has a certain amount of potential, right? So a certain amount of energy that can come out of it, and it can only give out as much energy as it took to heat it up. So that since the steel was easy to heat up, we say that it had a lower specific heat capacity, okay? It took less energy to heat it up, which means it holds less energy, so it can't deliver as much energy, right? It's only mildly going to, right, affect it, in this case, cool it down. The water holds a lot more energy, about more than 4 times as much between a lot of metals and water. So water is about 4,000 in terms of the joules per kilogram degree Celsius, or joules per kilogram one Kelvin, delta 1 Kelvin. So that 4,000 is the unit for water, and you're not going to see specific heat capacities bigger. Simply put, there's no substances, even other fluids, that have a specific heat capacity as high. Insulators, you may think maybe it's just metals because they're conductors of heat and electricity and so on. But no, even other substances have always lower specific heat capacity than water. All right, and so we say that the specific heat capacity of a material is the relative amount of heat needed to raise its temperature. Okay, per a certain amount, and of course it'd be per the standard mass kilogram. All right, so the specific heat capacity of a material is the quantity of heat needed to change a unit mass, there it is, of the material by a unit amount in temperature. For example, to change 1 gram by 1 Celsius degree. Okay, so that would be a unit of specific heat. Okay, it is a property of the material determined by experiment. Yeah, by the way, this is all empirical. People have collected it, kind of double-checked this data, and now we rely on certain, published values that I believe are probably periodically rechecked, but there's these certain agreed upon references for common substances. Okay, The specific heat capacity of water, this is a famous one, is, and many people test this one themselves, 1 calorie per gram degree Celsius, okay? And that specialized unit is called the calorie, all right? So the calorie is a unit of heat, okay? Which means it's directly related to joules, okay? It's just joules multiplied by some, equivalent, okay? And what it is the heat energy to raise the temperature of 1 gram of water by 1 degree Celsius, okay? We can then calculate how much heat must be absorbed by a material to change its temperature by a given amount, okay? So we see that we take mass, specific heat capacity, that's that letter C, okay? Remember C here stands for specific heat capacity. It's just a new constant specific to the material, it's our new thing, okay? But the formula Q is the quantity of heat, all right? Now you might be like, didn't he say it was energy? Why is it Q? Well, just to kind of separate it, that this type of energy does obey different rules, right? This isn't the energy of, say, a large moving object. It doesn't have kinetic energy, potential energy like a large solid object would. We're going to be talking about gases and liquids. So in that context, it makes sense, right? We want to give it a different letter, but it is still energy. It still has units of joules, okay? So, all right, this idea then of flowing temperature, heat flow will always go from the higher temperature to the lower temperature, okay? All right, heat added increases temperature and heat removed decreases it, all right? Heat and temperature are not the same thing. I probably made that really clear, haven't I? Temperature is a quantity that tells us which direction the heat will flow, okay? So we see with that zeroth law, it tells us that until equilibrium is reached, we know that the temperature that's lower will go up, the temperature that's higher will go down, because they ultimately have to reach the same number, okay? So that's guaranteed. There's a net change of temperature in that way. But the temperature is not flowing, temperature's changing, it's possessed by the object. We know it's the heat that's flowing, okay? Heat has a good comparison to work, because in those mechanical systems that were simple, we had objects that could gain potential energy, which is mgh. They could gain kinetic energy, which was 1/2 mv squared. Think like a pendulum, right? Well, what was the relationship between them? How could you apply a force to change that system? You did work, okay? So work could be done on the pendulum, but the pendulum could possess gravitational potential energy. The spring with a mass attached to it could possess elastic potential energy, but work was done on the spring, right? The spring never possessed work. Same idea here, right? When we talk about big, pinkish colored blocks and blue blocks, and we talk about water, cups of water, we'll say that they contain energy, but we never say they contain heat. Heat will flow between them and something else, okay? So when an object goes through a change of phase, I talked about this, and I wasn't seeing in the body of the text, but here we have the concept that we have a change in state of matter, okay? That has its own energy, which is also measured through experimentation and specific to every material. Some of them are famously large. Water has some big numbers all across the energy spectrum in terms of seeing that it has the highest specific heat of any substance. I guess liquid ammonium, I guess, is comparable, but I mean anything that's even close, right? But so water has this this incredibly high specific heat. It also has incredibly high energies to go, especially to go from its liquid phase to its gaseous phase, to vaporize. So you have a huge amount of energy required, or a very large value for the latent heat of vaporization, which is a number you look up in a table, a number given in joules per kilogram, or maybe calories per gram. Maybe you have to convert, okay? So that's the idea, very similar to specific heat. Okay, specific heat was joules per kilogram, right? But also had per degree change, because that's what it was. You actually were looking at how much degree change there was. Here's the formula, right? Q equals mc degree change. So now we have a new quantity, latent heat, and latent heat is just L equals, right? So rather Q, still Q. So Q equals M times L, all right? So I don't have the ability to write this time, so you're gonna have to take my word for it. Q equals M times L. Maybe I'll come back around to it. It's not like it's from our last lecture on heat. Okay? So here we have a specific heat capacity, and we may see it upcoming. All right, of 0.5 calories per gram. This is for ice. All right, how much heat would it have to be added to 200 grams of ice for it to reach a temperature of -10, or just a net change of -10? We don't know where it started or where it finished. We just know it remains ice the whole time. So it's definitely finishing somewhere below 0. So maybe its final temperature is -1. I don't know. Okay, but we just know there's a change in -10. Okay, we need the mass. Okay, and this quantity is based on calories. So that's fine because all of our options are going to be calories. So we don't even have to worry about converting to joules. I haven't shown you the conversion yet. Okay, so it's good we're not asking it of you. By the way, this value right here, 0.5, that would be in the measurement system I mentioned a couple times, that would be 2,000 joules per kilogram degree Celsius, because that's about half of what water is, which is the 4,000. Okay, so big number for water, half that for ice. Here in the calorie system, it's 0.5 because this whole calorie system is, specialized water where exactly it's 1 calorie per gram degree Celsius, or change of 1 Kelvin for the specific heat of liquid water. Okay, but here it's not liquid; it's a solid, and it doesn't hold its heat quite as well. That liquid phase is the best one apparently. Okay, so you got your answers. By the way, if you need a hint, there's the formula: Q equals mc delta T. And what are you solving for here? Q. You don't even have to rearrange anything. That's fine though. It's a great place to start. Okay, so hopefully you worked this out, identified your unknown, all right, and found out that it was 1,000 calories. All right, answer is A. Nice. Okay, so now we do have a latent heat question. So I think we'll see that letter coming up in the formula here. So if the latent heat of fusion of ice is 80 calories per gram, so that's a big number, isn't it, right? Because we just saw 0.5 calories per gram, okay? But that was degree, right? Degree. This is just mass because this is the phase change. And phase changes are like a big cliff to overcome. So if you think of the energy it takes to the heat of substance up, it's linear, and that's what the formula tells us, right? We have that directly proportional to delta T. So you get this linear increase, so it requires energy. You gotta go uphill as you get hotter and hotter and hotter. But then when you get to a phase change, you got a cliff to climb. When you get to that next phase, you've got that gradual incline again. So that's as you stay in that phase. But any phase change, those being from solid to liquid, which is a melting or vaporization is what I'm thinking of, to go from latent heat of vaporization, latent heat of fusion. Okay, so the latent heat of fusion is the one that refers to the change from going from a solid to a liquid, or from a liquid to a solid. So the latent heat values that you look up in the table, they always refer both ways. There may be some exotic substances out there, and I've always meant to look it up, that are anisotropic. They're different one way than the other. So there's a very noticeable different amount of energy. But that also, I think, goes against some ideas of how phase changes work, because why would that happen? Where did that energy get stored in a sense? So regardless, in this case, you just need to multiply the mass, okay, by the number given, the constant. The latent heat of fusion value you're given with units of calories per gram is 80. Okay? All right, I think we got it. It is 1,600 calories, right? And you can see, indeed, there it is, L, uppercase L. The subscript here, F, is referring to the fact that this is a fusion latent heat as opposed to the vaporization. Those are the names given to the two, okay? All right, every substance has two. How much heat would have to be added to 200 grams of ice initially at a temperature of -10 Celsius to completely melt the ice? So this is a good one, because you got to do both now. Find out how much energy it takes with the specific heat formula, so the Q to go from -10 to 0, and then as soon as you hit 0, you got to climb that cliff. So then take that mass, multiply by the latent heat of fusion. You've already been given all the numbers. You refer to the back to the previous ones, and we should work it out. By the way, these are the numbers you'll need. You're going to need the 0.5, because that's going to be the heating the ice. And then you're going to need the 80, okay, with the appropriate units, right? The first one being calories per gram degree Celsius. The second one just being calories per gram. All right. Specific heat, latent heat. All right. You ready for the answer? Do you know work it out? Okay. There it is. 17,000 calories. Answer D. 17 kcal. 17 kilocalories. All right. All right. So that's going to leave it off. We'll talk next time about the first law of thermodynamics, starting with an experiment where we saw mechanical energy becoming heat, which is usually not what we care about. We care more about heat becoming mechanical energy, but it's a good starting point, right? It proves an idea. Joule's famous experiment. There's the namesake. So I'll see you all next time. I hope this introductory lecture on defining temperature, heat, and specific heat capacity, as well as latent heat capacity, was interesting and informative. Thank you so much for watching.